the stress strain curve for concrete. Okay, so if you see this stress strain curve, then if the FCK, this is the graph for FCK. If you observe this graph up to the strain value of 0.002, it is parabolic. This is parabola, not linear. It is parabolic because it is for concrete. And then from this point, the graph is straight line. Okay, so this is the graph of concrete, stress strain curve for concrete. And if we mark the typical points, we have taken only two strains. That is, first is the 0.002 and second is the 0.0035. Now, why 0.002 and 0.0035? Because this is the axial strain or compression strain. This is the maximum strain that we are going to take in the axial compression. And when a member is subjected to axial compression as well as bending, then this strain is considered 0.0035. Okay, so here if we show this, then 0.0035. Okay, this is for axial compression and bending both, and this is for purely axial compression. Now, if you, as I have told you earlier, the factor of safety for concrete is taken as 1.5, and for steel, the factor of safety is 1.15. Okay, so if you are having the calculator, you may know that for taking the stress in steel, we always take 0.87 Fy. In the formula, we always take 0.87 Fy. So where from that 0.87 comes? So if you divide that Fy divided by 1.15, if you do, that is 1 divided by 1.15, you can do it on your calculator. You will get the value as 0.87. So that coefficient 0.87 is nothing but when you divide the strength of the steel by its factor of safety, then you will get 0.87. Similarly, here in the limit state method also, this is FCK, and the factor of safety for steel we have taken as 1.5. So if you divide the FCK by 1.5, then it is 0.67 FCK. So, but for the concrete, it is recommended by the IS code that again you divide this 0.67 by 1.5. So if you again divide this 0.67 by 1.5, then you will get the value 0.446 FCK, 0.446, and that 0.446 is to be taken into the consideration, this 0.446, and this 0.446 is nothing but the maximum stress in the concrete, because this axis shows us the stress, this is the y-axis stress, so this is the value of stress. Okay, so for the strain of 0.0035, we are going to take the maximum stress in the concrete is 0.446. Okay, so this value will be required in further calculation. Here you can see over here 0.446. Okay, so this is the typical stress strain curve for the concrete. Now we will move further. We will see how the stress block parameters are there for limit state method, that is strain diagram, stress diagram, and what is exactly this limit state method and how to calculate the compressive and tensile forces. So here you consider a beam cross section. This is the beam. This width is B. So the width of the beam is B. Its effective depth is D. I hope I have cleared with you what is the effective depth and what is the overall depth. Overall depth means from this corner to this corner. This total depth is called as overall depth, and we always denote this overall depth by capital D. But from top to up to the center of this reinforcement, that is the center of the bar, this is nothing but your effective depth. Okay, so your effective depth is small d. This is as usual our neutral axis, which is passing through the centroid, and every fiber on the neutral axis does not experience any force. Then the distance of this neutral axis from topmost fiber, that is fiber which are situated at this level. From topmost fiber, the distance of the neutral axis is considered as this distance is xu. Okay, so this distance is xu. Xu is the term which is most popularly used in limit state method to show the depth of neutral axis. Okay, particularly you have to use this notation only. So XU in the limit state method always indicate the depth of the neutral axis from the top. Now, if we draw the strain diagram, okay, if we draw the strain diagram for upper part, so in last lecture itself, I have told you the fibers or the molecules or the elements above the neutral axis are always subjected to what are always subjected to compression, and here at below tension is there. That is why at the bottom we always provide the steel. So now here, if I draw the strain diagram, then this is the strain diagram. Okay, so at the neutral axis it is zero, as we assume that it does not experience any stress, any force, nothing is there. So uh, and this is the triangle. So here, as we have taken the in the stress strain curve for concrete two strains, that is 0.002 and 0.0035. 0.0035 is the maximum strain. So here the maximum strain is 0.0035 maximum strain, and before that, one strain at some point, let us assume at a distance x1, the strain is 0.002. Okay, so we assume that the distance between these two strains, that is this vertical distance between these two strains, is x1. We don't know what is the value of x1. Similarly, we assume that from neutral axis, this 0.002, whatever uh, maybe the height, we don't know what is the distance. So we assume that it is as x2. Okay, we assume it as a x2. Now this is our strain diagram, a simple strain diagram. It is not very difficult. Now if I move further to draw the stress diagram from this strain diagram. Okay, so here some terminologies are given. What is x1, x2, which I have told you right now. So I have told you D is the effective depth, x is the neutral axis, FCK is the characteristic strength. You already know that. Now here, x1 is the height of rectangular block of the stress diagram. Okay, and x2 is the height of parabolic block of the stress diagram. Now here you observe this. If you observe this curve is parabolic from this to this point, that is from 0 to up to the strain of 0.002. The curve is parabolic, and after that it is straight line. Now if you see over here, so here is the value 0 and here is the value of strain is 0.002. So in between these 2 points, now if I want to draw the stress diagram, then it must be parabolic. Okay, so this is parabolic. Now after that, from 0.002 to 0.0035 it is straight line. So this line is straight line. So your stress diagram is from in the region of x1, that is this x1. This is x1. Okay, so this is x1. In the region of x1 it is straight line, and in the region of x2, that is here, it is parabola, because it is the graph varies in this way. Okay, so this is your stress diagram. So this is the straight line, and after that it is parabolic. Okay, so here at the level of steel, if I project this AST, at the level of steel, these lines over here, projection, then you always know that steel is always carries tension. Okay, concrete is very strong in compression but weak in tension. That is why we always provide steel in the structural member. So it resists the tensile force. So here, this is the TU, that is your tensile force in the steel, and here the tensile stresses are developed at the bottom. So therefore, we have shown here the force TU, tensile force, and above the neutral axis, compressive stresses are developed. So here somewhere we have assumed that in this whole region the stress is compressive, and the CG of the whole region is somewhere here. We don't know exactly where is the CG acting, and through that CG the compressive force is acting. See, whenever you say that the compressive stress is acting, so uh, on the contrary, we are having area of cross section, we are having compressive stress, so we can say that somewhere uh, at the CG, compressive force is acting. Okay, so this is the CU, that is the compressive force which is acting over here. Yet I am telling you, we have not exactly calculated the position of this CU, where it is exactly acting. This is just a diagram. I am just saying you. But here we know the exact position of this force TU. because where it will act from the level of steel. See, the level of steel is here. From top, if you see, the level of steel is at a distance of small d. So from top at a distance of small d, this tensile force is acting. However, we need to calculate that where is that compressive force is acting. Okay. So for now, the next thing is here. So if you see the strain diagram, the previous diagram, just one minute, previous. Here, if you see this triangle now, okay, if you see this triangle now here, these two, this is a small triangle and this is quite large. So here these two triangles are similar triangles. Okay. Now if we apply the property of similar triangles over here, then what do we get? So xu, if I take this xu, x2 divided by xu must be equal to 0.002 divided by 0.0035 by the property of similar triangle. We already know this, very simple. So here in the next slide, that is what is taken into the account. See here, in the next slide, that is x2 upon xu is equal to 0.002 divided by 0.0035, which again comes 4 by 7. Okay, 0.002 divided by 0.0035. If you are having calculator, you can check it. So it comes 4 by 7. So from that we will get one relation. X2 is equal to 4 by 7 of x0. From that we will get one relation, that is x2 is equal to 4 by 7 x2. But we know that xu is equal to x1 plus x2. Okay, as we have seen in the previous diagram, from top, whatever our straight line is there, that portion, that area is x1. From below that, whatever our parabolic part is there, that is nothing but our x2. Okay, and the total distance is from topmost fiber to the neutral axis, that is xu. So x1 plus x2 is nothing but x. So but we know that now the relation x2 is equal to 4 by 7 xu. So just the value is we are going to put the value over here. So xu is equal to x1 as it is, and x2 is 4 by 7 x. Okay. So for this now, if you shift this term to this side and take the xu common, then you will get the value x1 is equal to 3 by 7 x. So now we calculated x1 and x2 in terms of xu. Xu means what? Remember, xu means the distance of neutral axis from the topmost fiber. Okay, where the neutral axis is situated, that is nothing but xu. So now we have got the value of x1 as well as we know the value of x2. Okay. Now next, area of the rectangular part, that is base into height. Okay. So the area of the rectangular part is calculated now. So I think we have to go to the previous slide to understand this. Just a minute. See here. Here, this part, this portion is our rectangular part. Okay, because this portion is straight line from point 2 to 0.002 to 0.035. So this is our rectangular part. Okay. Now if you see this rectangular part, what is the area of this rectangular part if I want to calculate the area of this rectangular part? So what is our maximum stress? It is 0.446 FCK. For the strain of 0.0035, our maximum stress is 0.004 FCK. So the area will be 0.446 FCK into x1. This is nothing but our area. Okay, and similarly for parabola also we can calculate the area. What is the formula for parabola? It is 2/3 base into height. So we know the base again, the same value, and height is also known to us. So that we will see next step. So here the value is, here if you see the area of rectangular part base into height, so the base is 0.446 FCK into height is x1. So here the value of x1 is 3 by 7 x2. Height is x1, so value of x1 is 3 by 7 x2. That value is directly kept over there, and so we will get that area as 0.19 FCK into x2. This area is required to calculate ultimately the what is the compressive force acting over there. So this is 0.19 FCK into XU. Now the area of parabolic part is 2/3 base into height. Okay, so 2/3 base into height, base is 2 by 3 into 0.446 FCK into 4 by 7x. So height is x2 again. Okay, for parabolic part, as I have told you earlier, height is x2. For this part, rectangular part, the height is x1. So if you put 4 by 7 xu, then you will get the value 0.17 FCK into x. Okay. And if we want to calculate the total area, then we have to add these two areas, area of rectangular portion and area of parabolic portion. So if we add these two areas, then we will get the final value as, if I add 0.19 FCKXU plus 0.17 FCKXU, if you add these together, then you will get 0.36 FCK into x. Okay, 0.36 FCK into x. Now you focus on this term 0.36 FCK. Okay, so 0.36 FCK is nothing but a sort of stress which we are getting there, where maybe the compressive force is acting, because this value will come in between the uh, in between that portion of 0.002 to 0.0035 step. So the corresponding value, whatever we are getting for that force, it should be less than 0.446 FCK. So our calculation is correct. We have got the value of 0.36 FCK. Now the compressive force is again nothing but it is stress into area. So we will go to the back side. So see, if I want to calculate the force here, that is the compressive force Cu, force is nothing but stress into area. Just now we have calculated that 0.36 FCK is the stress and nothing but, and here above the neutral axis, if you see this area, so this area is B into XU. The area is B into XU. So here the total whatever may be the force required, that can be calculated as the compressive force is XU is equal to 0.36 FCK XU into P. Okay, so this is the total compressive force which we are getting here. Now similarly, if you want to calculate the value of TU, TU is nothing but the tensile force. The basic formula to calculate the force is nothing but stress into area. So what is the stress? So let us say this is the steel. Let us assume Fy is the yield stress of steel. Fy notation. Y is the suffix. Okay. So divide that Fy by 1.15. So what is the value then? 1 divided by 1.5, we will get the value 0.87. So 0.87 Fy is the stress. Okay. And then what is the area? So for area, we need to calculate the area of the steel. So we say that area is AST, area of the steel, whatever may be the area, n number of bars may be there. Okay, so AST is the area. So if we put together that formula, then we will get ultimately force is equal to stress into area, which is equal to 0.87 Fy into AST. That is nothing but the tensile force. So here now after this we can calculate what is the distance of this compressive force Cu which is acting over here. So if we calculate the distance from topmost fiber, then we will get the position of this force, Cu force. Okay. So to calculate that, we are going to use the simple formula. We know for to calculate the y bar, the formula is a1 y1 plus a2 y2 divided by a1 plus a2. Okay. So first area is your rectangular area. See here, first area So this is your first area. This area is the rectangular area. We already know the area of this. Okay, and we already know the distance. This length is x1. This length is x2. We already know this area. So we can easily find out y1 and y2. We can consider y1 and y2 from topmost fiber. Okay. So now here in the similar way, we can take the value of y1 as it is x1 by 2. Okay. So here y1 means what, from topmost fiber distance of the centroid of this rectangle. So this total is x1. Then the half of that will be x1 by 2. And what will be the value of y2? So now y2, if you see that this is the like it is a parabola. Okay, so for the centroid of the parabola will be at a distance of 3 by 8 x cube. Okay, so this centroid will be 3 by 8 x cube. This is the formula you have already learned in CG and MI first year. Okay, to go through this formula. So it is 3 by 8 x cube from this end. Okay, from this end. So now if we want to calculate the y bar from the top, then it will be x1 plus 3 by 8 x. So the same values we have considered over here. In the next slide, just a bit. Now here, A1 as we have calculated 0.99, sorry, 0.19 FCK into x cube, y1 x1 by 2, A2 0.17 FCK x cube, and y2 x1 plus 3 by 8 x cube. If you put all these values together, in the formula, then your formula becomes y bar is equal to 0.19 FCK xu into the further calculation is done over here. We have put the value of x1 and x2 also. Okay, x1 as we have calculated the relation between x1 and x2 and also x2 and x2. So after putting all these values, we will get y bar is equal to 0. Here y bar is equal to 0.4166 x cube. This is what is the value of y bar, and if we round this the next digit, then y bar is equal to 0.42 x. Okay, this I have already told you. So T is equal to tensile stress into area. T is equal to 1 upon 1.5 into Fy, where Fy is the yield stress in strength of steel. Then AST. So AST is the area of steel. So if you put all these values together, then you will get T is equal to 0.87 Fy into AST. Okay, so here, if I show you in the previous slide, you see this previous slide, this compressive force which is acting over here, this tensile force is nothing but 0.87 Fy into AST. This is the magnitude of this tensile force, and the magnitude of this compressive force which is acting over here is 0.36 FCK, 0.36 FCK, and the area is B into X. Okay, so Cu is nothing but 0.36 FCK B into X. This is the total compressive force which is acting over here. So now, one more important thing you must remember over here, this the location of this compressive force. From top, it is located at a distance of 0.42 x. As we have calculated right now, the position is 0.42 x. Okay, so moving to the next. Here some detailed calculations are there. That calculation is again shown here. So we have already gone through this. Then some important points for the limit state method. The limit state method is based on the partial safety factors for the concrete as well as steel. This method takes into the consideration the ultimate load which is obtained by multiplying the load factor to the working load. Okay, load factor to the working load. Load factor means factor of safety. Yeah? Okay. So the strain value, the strain value of stress strain curve in the compression is 0.002. So only in axial compression it is 0.002. The maximum. This question may be asked for MCQ, and in that MCQ, both the options may give to you 0.002 and 0.0035. So you have to remember this value. Only in pure axial compression, the strain will be 0.002. And when there is a combined, that is compression is also there and bending is also there, then the value is 0. Here, when compression is also there and bending is also there, then the value is 0.0035. Okay, so these are some of the important points related to first topic, first chapter. In the first chapter, you remember one thing: there will not be any numerical in the exam from the first unit. From the first unit, there may be two or three, hardly two questions. That two of the MCQ they can ask you in the exam, and in the MCQ also these types of questions will be there. What is the value of XU from the top? That is this 0.42 XU, or what is the tensile force? That is 0.87 FY into AST. Whatever we have seen, those types of question may be there in the exam. Even in the exam, the definition such as load factor, characteristic strength, up till now it is not asked. Okay, so as it is a design paper, this is the very small unit and very small introduction. Basically, to that unit, what you need to understand that just understand this structure and this. Remember, this is the standard stress and stress distribution diagram. You remember this. This is suggested by IS code. IS code also gives the same diagram and same graph. This variation, this stress strain curve variation, all these are the experimentally determined curve. Okay, so these are the standard values which are where is the mouse? All these are the standard values which are recommended by the IS code. And here you remember this thing: what is the value of this force Tu? Where is this force Tu is acting? So Tu is nothing but tensile force, which should always act at the bottom, and it is acting at the level where the steel is situated. Okay, it is acting at the level of steel. Okay, so at this point it is acting. See here, I have not shown this Tu force over here at the bottom of the beam. It is not shown here. It is shown at the level of the steel Tu force. And already we have seen the formula for Tu force: 0.87 Fy into AST. Similarly, here Cu force we have also evaluated. The value of Cu force is 0.36 FCK B into XU. This is the value of Cu force. Then we know the position of Tu, but we don't know the position of Cu from top. So we have calculated the position of this Cu force from the top by simple formula to calculate the Y bar. So from that we get the value. It is 0.42 XU. So this value is 0.42 XU. Now see, this is the compressive force. This is the tensile force. So the distance between these two compressive force and tensile force, it is called as lever arm. It is called as lever arm, and that value of lever arm, it can be calculated as T here. This distance from this point up to the top, this total distance is D. So from this point to this point, this total distance is D. From that D, if we minus this one, then we will get this lever arm. So from D, if you minus 0.42 XU, so this lever arm will become D minus 0.42 XU. Okay. So this is the value of the lever arm, D minus 0.42 x. Sorry, I have seen the message lately. My voice is not clearly audible. Is it audible now? Hello? Hello?
Yes, sir.
Is it audible now? I think in between somewhere range problem was there, I think so. So right now in the first unit, you just remember these are the key things. Whatever I am showing here, you just focus on this. Whatever we have studied here right now within these 10 to 15 minutes, that is the idea to introduce first chapter over here. Okay, so you understand these terminologies. These all these are even notations are also standard. Okay, nobody change the notation. You can go to any book, you will always get the depth of this neutral axis by this notation x. Okay, so now key points to remember, I already told you. You should go while studying this unit, you must all should know these values. And now it is very easy. You have seen that how we can calculate the value of tu, how we can calculate the value of cu. However, you know the concept, you know the logic now, how those values are calculated. It is very good, but still you need to remember these values of cu and the formula for t, because later on this diagram is only for singly reinforced section. We can say that this is singly reinforced section. Singly reinforced section means steel bars are placed only at bottom. Although there are anchor bars maybe there in the beam, there is no uh, a beam cannot be cast with the steel at top. There may be two bars of 10 diameter which we have to place compulsory at the top of the beam, but those two bars are the nominal bars. We have not calculated separate bending moment for those two bars to provide in the compression zone. Okay, so here if you see the ultimate resulting diagram, so we can say that these bottom bars, these bottom three bars which we have provided, to provide these bottom three bars, first of all we need to calculate what is the load coming on the beam, and after that we need to calculate what is the bending moment of the beam, and after the calculation of the bending moment we are going to provide the steel bars. Okay, so that is not the case over here. Although in practically in actual beam the bars are there, anchored bars are. So this type of section is called as singly reinforced section, and this is the typical stress strain diagram for the what we can say singly reinforced section. Strain diagram is always remain same, but the stress diagram may get changed little bit. Not it does not change its shape, but it changes in terms of the forces when you go for the doubly reinforced section. That we will see later on when we will study the doubly reinforced section. Right now, important point is for you to understand this diagram. Why from this here to here it is a straight line, why it is parabolic. I have already explained you by taking the reference of this graph. Then the maximum value is taken as 0.446 FCK. I have already told you this is the standard value suggested by the IS code. These are this is the standard graph. So we have to take the centroid from the top. It is y bar, that 0.42 XU that we have already seen. So now after this, we have see if we see further. These are the some questions which may be asked in the examination based on this topic. Okay. These are some MCQ questions that can be asked. So here, if you see, the ratio of the question is the ratio of ultimate load to the dash dash is called as the load factor. Okay, so I will erase these annotations first. Just wait. So now here if you see the ratio of ultimate load to the dash dash is called as load factor. Load factor means it is a factor of safety, that is called as load factor, and it is taken as the ratio of ultimate load to the working load. Okay, it is taken as the ratio of ultimate load to the working load. See, what is the meaning of ultimate load and what is the meaning of working load? I will tell you. Suppose now a structure is there, or a beam is there, or any structural component is there, and on that 100 kilonewton load is acting. Okay, practically on that structure, if you evaluate all the load and you found that 100 kilonewton load is acting, for example, take some value 100 kilonewton load is acting, but while actually when you are actually start to design that structural member, you consider some factor of safety from your side. You won't design that structure for 100 kilonewton, although you are knowing that on that structure 100 kilonewton load is coming. Okay, so we design that structure for higher value than 100 kilonewton. Okay, so therefore in future, suppose due to some any reason, if the load increases on the structure, then it should not fail, or it won't fail. What is the this XU? What is FCK X1 X2? Have you written that? Yes, no, fast.
Yes, sir.
So now below this diagram, write down below this diagram a typical strain diagram and stress diagram. Write down. I will repeat it. A typical stress diagram and strain diagram for singly reinforced section is shown above. Is shown above. The next line, write down. The total tensile force is equal to the total tensile force, in bracket write down TU. Notation of that force is TU. Capital T, small u. U is the suffix. TU is equal to stress into area is equal to 0.87 Fy into AST. 0.87 Fy into AST. Next line, write down where Fy is equal to yield stress in steel. AST is equal to area of steel. AST is equal to area of steel. Next line, write down the total compressive force in bracket Cu. The total compressive force in bracket Cu is equal to 0.36 FCK. 0.36 FCK V into XU. 0.36 FCK V into XU. Cu is equal to 0.36 FCK V into XU, where where B is equal to width of the section, XU is equal to depth of neutral axis from top, XU is equal to depth of neutral axis from top, and you know the FCK is the characteristic step. FCK is the characteristic step. Okay. And now next line write down. The compressive force or the centroid of compressive force is at a distance of 0.42 XU is at a distance of 0.42 XU from the top. On the next line write down. Write down on the next line. The lever arm that is the distance between compressive and tensile force is denoted by letter Z and it is equal to in bracket write down Z is equal to D minus 0.42 XU. D minus small d, write down small d, is equal to D minus 0.42 XU. D minus 0.42 XU. Where, next line write down, where small d is equal to effective depth of the section. Small d is equal to effective depth of the section. Now write down this. This is also important. In exam, these questions may be also asked. The rectangular area of rectangular part, area of parabolic part. So write down this. This is also very important. Shall I dictate or you will write down by your own?
Dictate, sir.
Okay. So on the next line write down. From the similar triangles, त्याच्याच पुढे ब्रॅकेट मध्ये लिहा रेफर स्ट्रेन डायग्राम. So just put a bracket मध्ये write down in front of that bracket refer strain diagram. Next line लिहिलंय, it is clear that comma it is clear that comma x2 upon xu is equal to 0.002 divided by 0.0035. Next line write down, by rearranging the terms we will get xu is equal to 4 by 7 xu, x2 is equal to 4 by 7 xu. x2 is equal to 4 by 7 x. Next line write down, from the diagram it is clear that xu is equal to x1 plus x2. xu is equal to x1 plus x2. xu is equal to x1 plus x2. Next line write down, by putting the value of xu by putting the value of x2 we will get x1 is equal to 3 by 7 xu. x1 is equal to 3 by 7 xu. Next line write down, by referring the stress block diagram area of the rectangular part by referring the stress block diagram, area of the rectangular part is equal to area of rectangular part is equal to base into height, base into height, which is equal to 0.446 FCK, 0.446 FCK into x1, 0.446 FCK into x1. So next line, put the value of x1, it is 3 by 7 xu. Put the value of x1 is 3 by 7 xu. So finally, you will get area of rectangular part is equal to 0.19 FCK into XU. FCK into XU. Similarly, area of parabolic part is equal to area of parabolic part is equal to 2/3 base into height. 2/3 base into height. So it is 2 by 3 into 0.446 FCK into x2, that is 4 by 7 XU into x2 म्हणजेच 4 by 7 XU. So if you put all these values, you will get area of parabolic part is equal to 0.17 FCK into XU. 0.17 FCK into XU. Now if you add total area, it is 0.36 FCK into XU. It is 0.36 FCK into XU. As here in every calculation we consider B as a unit. So finally, write down next line. Finally, the compressive force Cu is equal to 0.36 FCK, 0.36 FCK B into XU. .36 FCK B into XU. Next line, write down. Location of or the centroid of compressive force Cu. Compressive force Cu. Okay. Write down on the next line. Consider the reference axis Consider the reference axis is at the top. Is at the top. Next line write down. We know that we know that y bar is equal to a1 y1 plus a2 y2 divided by a1 plus a2. Where on the next line write down where a1 is equal to, this is the value of a1. a1 is equal to 0.19 FCK into XU. 0.19 FCK into XU. A2 is equal to 0.17 FCK into XU. Y1 is equal to x1 by 2. y1 is equal to x1 by 2, which is again equal to, what is the value of x1? It is 3 by 7 x cube. So your y1 will be 3 by 14 x cube. Is 3 by 14 x cube. Next line, y2 is equal to x1 plus 3 by 8 x cube. x1 plus 3 by 8 x cube. For this 3 by 8 x cube, you go through the formula for the centroid of parabola. Okay, centroid of parabolic curve. When the parabolic curve is their total parabola, that is what we draw the bending moment diagram for the simply supported beam carrying UDL. You will see the parabola WL square by 8 is the moment at the center. If you cut down that parabola from the center, okay, then and if you extend the topmost line and or adjoining line, you will get one curve in between that portion. Okay, and formula for CG of that portion is, from left hand it is 3 by 8 x cube, from right hand it is 5 by 8 x cube. So you just go through that formula. So y2 is equal to, it is now x1 plus 3 by 8 x2. So put the values of x1 and x2 over here. x1 is 3 by 7 x2 and x2 is 4 by 7 x. And now after this, so put all these values in the formula. Y bar is equal to write down all the values. First, a big square bracket. In that, write down 0.19 FCK XU, that is area, into Y1. Y1 is 3 by 14 XU. Square bracket complete. Plus, this is your first term A1 Y1. Plus, now we will introduce A2 Y2. Again in the square bracket, write down A2, the value of A2, 0.17 FCK into XU, 0.17 FCK into XU into now write down y bar is equal to 0.42 XU. Y bar is equal to 0.42 XU. From top here, you should write down in front of this from top or from topmost fiber. From top or from topmost fiber. Okay. Write down two important points. In the next time you write down important points to remember. Number one, important point to remember. Number one, in the stress strain curve of concrete, in the stress strain curve of concrete, the maximum value of strain, the maximum value of strain under compression, under compression is taken as is taken as 0.002. Second important point,
सर फर्स्ट पॉइंट परत रिपीट करा प्लीज.
okay, so I will repeat the first point. In the stress strain curve of concrete, in the stress strain curve of concrete, in the stress strain curve of concrete, the maximum strain value, the maximum strain value for the compression, for the compression alone, for the compression alone, for the compression alone is 0.002, is 0.002. Full stop. Point number second, in the stress strain curve, in the stress strain curve of concrete, in the stress strain curve of concrete, the maximum strain for for compression and bending for for compression and bending for compression and bending, it is taken as 0.0035 0.0035. एक लाइन छोड़ा and left one line, and on the next line write down, this is for your reference, write down, the above two values are given by IS 456 2000, IS 456 2000. For to be considering as the standard value. Now already we have discussed this first time. So now already we have discussed MCQ number 1. I was about to told you that the ratio load factor is nothing but factor of safety, which is the ratio of ultimate load to the working load. Working load means what? You suppose a structure carries a load of 100 kilonewton, or a 100 kilonewton load is acting on that structure. Then that 100 kilonewton is nothing but the working load. But while actually designing the structure, we won't design it for exactly 100 kilonewton. We design it for say 120 kilonewton, 130, 140, 150, anything above 100. We for that we design the structure. Why we are designing the structure for higher load? Because in the near future, suppose after 5 years, 10 years, 15 years, if the load on the building or if the load on that structure is increased, then that structure should not fail. It must sustain. Okay. And from civil engineering point of view, when we design any structure, we at least keep its duration for 50 years. Okay, you assume that for 50 years at least we have to think about its strength and stability. Okay, so that is why we increase the working load. Now if the factor of safety is 1.5, we multiply that working load by 1.5. Now in our example, if we multiply that 100 by 1.5, as we have assumed that 100 is our working load, so our ultimate load will be 150. So the ratio of this ultimate load to the working load is nothing but our what we can say load factor or factor of safety. Now the next MCQ. The characteristics load has a dash percentage of probability of not being exceeded during the life of structure. So the characteristics load has a 95% of probability. Okay, so which strength if not being exceeded during the life of structure. So we know that it's 95%. I already told you. In the design of stress block, the area of rectangular part is dash. So in the design of stress block, area of rectangular part, the options are A 0.17 FCK into x cube, B 0.19 FCK into XU, C 0.67 FCK into XU, and D 0.87 FCK into XU. So as we have seen the derivation for the design of rectangular part, your area is 0.19 FCK into XU. Your area is 0.19 FCK into XU. Okay. So in the design of stress block, the parameter here. Okay, in the design of stress block, the area of parabolic part is. So in the design of stress block, the area of parabolic part is okay. So here the area of the parabolic part, if we want, then that is 0.17 FCK, 0.17 FCK into XU. This is the area of the parabolic part. So now the next question: total compressive force in a stress block diagram is given by. So the total compressive force, the options are 0.17 FCK XU into B, 0.19 FCK XU into B, 0.36 FCK XU into B, and 0.67 FCK XU into B. So the answer is 0.36 FCK XU into B. This is the correct answer. Okay. So now with this, your first unit is over here. Now I will share this PPT to you along with this video lecture on the WhatsApp group. I will share today up to evening, and I will also share that post lecture what we have conducted, that introductory lecture. That also I will share with you. Again, you sit and go through these lectures. Okay. So once you go through these lectures, if you are having any difficulty now, see, we are having very limited time over here. So if you are having any difficulty right now on the WhatsApp group, my number is there, you can call me.